Thank you for inviting me. And I'm going to focus on a very different flavor, which is going to be about onboarding a community to use some of these technologies. And the very obvious thing some of you may think, are we reinventing the wheel somewhere? And that would be true in some cases, but in most cases it's not, and I'll explain why. Cyverse as a project, and I'd like to use the term ability and audacity. Some of you mentioned that today, because people learn to live in their laptop, and when they think of the cloud, they think of taking their laptop in the cloud and then maybe making it bigger, and the results are not always the same. And somehow allowing the science community, especially the ones that I represent, which is life sciences, to think bigger than what they normally do is an important aspect. So our project is focused on that, and then at the end, what I would like to sort of ask you is give us feedback on what can we change, especially as we build global communities. So I want to talk of the innovation life cycle and what happens in our labs. It's an important thing for some of you to consider, those of you who haven't spent much time in academia, as to what are the barriers to some of these things, and then what is it that sort of is important for adopting technology. And then a topic that's really close to my heart, which is computational thinking and why it matters, especially for domain sciences. And then the motivation and platform for why we build this and how we are trying to democratize the innovation and computation for our users. And what is pragmatic infrastructure for domain science in today's day and age, which you have so many options. And then what are the problems you're trying to solve? And then finally, what are the challenges in collaboration? And these are the things that we are not really good at, as in we, I mean myself and my team and my community, and I'm looking for better ways of doing this. So here is sort of a very simple formula for success in our labs. You have some bright, very energetic undergraduate or graduate student who reads a paper, gets really motivated, comes to the lab meeting and says, I read this, it's phenomenal, we need to go after it. And then you look at them and then you sort of say, there's enthusiasm, I shouldn't kill that. Let them read a little bit more. And then somebody tells them, you should put that in the cloud, that analysis will just work perfectly. And then there'll be fame and fortune to be had, and we'll all be famous. That sort of is a bi-weekly occurrence in many labs. The reality sort of starts this way, where you have somebody gives you some Excel, some R, some Perl, Python, you name it, and it's all there. And then, of course, you add the mix of, well, it needs some Microsoft, it needs some Apple, and of course, it needs Linux. And then you can run it in Amazon and Azure and Rackspace on your campus HPC, there's Xseed. And then you need a lot of glue to make it run. And then, of course, there's the big data landscape that you need to throw in to scale it out. What happens here is that I like to call the first author syndrome, because the person who wrote that paper, most likely the first author is the only one that can run that piece of code, and nobody else in that line can run it. They all know where the repository is, but nobody can really run it for the project. And so this young student starts sort of emailing the first author, doesn't get that, then starts harassing somebody else in the lab and says, I'm trying to run this on blah, blah, blah system, can you help me? And somebody helps them, some graduate student feels a little bit bad and says, okay, I'll spend the evening with you. And then slowly you realize that the social status of that poor student in the lab is going down. Nobody wants to make eye contact, nobody wants to talk to him or her. And then eventually they're like, screw this is not working at all. I'm just going to rewrite the software by myself. And that's where the sort of cycle repeats itself. And you realize that what was a very nice idea and somebody said, put it in the cloud, became something like this very quickly. And eventually that's what happens to the energy and enthusiasm of that bright student. And as you all know, especially in California, if you have to dispose this off, there's a lot more that you need to do than just put it into the waste bin. And so this is happening very frequently. And we sort of gotten good at that. Well, fail fast, fail often. And when you think of it, the part of winning, which you see right there, how losing can help you win. I think we need to do a lot more to allow our community to win, because the technology choices we have given them, the options that we are throwing at them, at the pace that we are introducing it, it almost is becoming impossible for them to win, because they just take the same problem and just move it to a different platform and expect different results. And that's not the way we really want to onboard communities. So here's sort of the investment in big data science from National Science Foundation that pays my bills. And so in 2006, they realized that the biological sciences, bio division, is making heavy investments in data acquisition. You heard of many, many genome projects and all of those coming out. And there's very sort of limited investment in analysis and data management. At the same time, the computer information science engineering, the SCIence side, was investing in different areas, especially in sort of the supercomputing tools, software, and he sort of started seeing the obvious benefits in geosciences and astronomy, groups that were very well tuned for large team science. They were already doing that. There were a handful of telescopes. In our case, there are many, many microscopes or many, many sequencers. So everybody was a data producer, a data generator, and what was happening is the bioscientists were not able to leverage the SCIence-funded sort of infrastructure, whether it's HPC or even a lot of the innovation that was happening sort of in the NSF realm. And so when they realized that, they said, what is the new type of infrastructure that we can put together? What is that will make it more welcoming for people, such that innovation that's happening in SCIence is reaching bio much quicker? And if you think in terms of sort of the startup mentality, here is NSF funding new awesome things in SCIence, but nobody else outside of SCIence is jumping on it, and they're just looking elsewhere and keeping the pace of innovation at the same level that it has been forever, and ignoring something like this that's happening pretty frequently. And so we really had to change that, sort of going back and forth. And so our project sort of took on that role in a way where we said, fine, we are going to take something that is not fully baked. It's almost there, but it's filling up an important niche area, and we are going to make it more useful for our community, such that we become the underwriters in a way of saying that, let's try this out, and if it works for you, we share it with more. If it doesn't, we write yet another proposal. But that sort of was what we were trying to do. So you sort of look at the life cycle where you have data to information and you have some infrastructure. The information to knowledge part is where you need a lot more training, and we sort of figured that we had to do infrastructure and training under the same umbrella, rather than say somebody builds infrastructure, somebody shows you how to use it, and somebody helps you end to end with it. And so that's we were born as iPlan Collaborative. It was a 5-year, $50 million bio-directed project in 2008. Our mission is to design, develop, deploy, and expand a national cyber infrastructure and train scientists in its use. And at the most fundamental level, our job was to democratize access to computing resources. There are many, many labs that are there that are brilliant scientists, but they don't know where to start because they have the data, they have a way of sort of doing something, but they don't know how to utilize other resources that are available to them at no cost. And so you sort of almost have to think in terms of when there's innovation and you have a group of people who are able to sort of corner that and utilize it, and then you have somebody else who's far away, doesn't know how to be part of that team, and then just sort of start doing something and eventually fade away. And this was a real concern, especially for me, and those of you who are part of large projects know it well enough that some of the bright ideas come from the single investigators who honestly don't like to talk to people. I guess most of us in academia are good at that, but in general, they're hanging out by themselves, doing awesome stuff, but what they do stays with them. How do you bring it to a bigger community? Again, that was sort of our focus. And so the project timeline is in 2008 and 9. We had sort of the grand challenge view. What do we need? How do we put it together? And then in the year 5, we were retasked to serve a broader life science community. And then 6 to 7 is when sort of we have seen rapid growth. Right now, we have about close to 40,000 users from around 36 countries, lots of data, lots of jobs, lots of fun things that I want to talk to you about. So we are a cyber infrastructure. There are platform tools, data sets, there's storage, compute, there's training and support, the standard tagline. This is sort of how we look at our platform philosophy. So we strive to provide the cyber infrastructure Lego blocks. And in Danish, that's Lagat, play well, and I put together in Latin, which is really important. We wanted our community to put together things that they need. And if a desired functionality is not available, they should be able to extend that using the CI components, much like the Lego blocks. And as you can see on the right-hand side, we sort of have the superheroes, and that's what we are striving to do with our community. And so through these extensible and customized platforms, creating sort of the ecosystem that allows you to move between, whether it's the storage, it's the compute, it's the sharing, and then benefit the broader community and not just few lab groups. And we were sort of seeing the digital divide in our community where groups who knew how to use high throughput computing, high performance computing were on a different sort of tier, and the others were just getting left behind and they were fitting in their laptop, and we had to sort of bring that close together. And then provide the tools to allow the community to manage their digital assets. Doesn't matter, it's in a commercial cloud, it's in your HPC, it's in your lab. How are you going to manage that and keep track of those things and then do something meaningful with it as a community, not just as an individual? At the end of the day, we want to improve computational productivity. That's where we are. Doesn't matter what platform, what tool, it's computational productivity. And so the paradigm shift sort of from my perspective was from producer to user. So right now we're in a sort of a beautiful time period where producers are the Amazons and the Googles and the Microsofts and everybody else, and they're driving a lot of the innovation. But end of the day, and those of you who haven't seen this book, it's open source, check it out. It's a really nice book from Eric von Whipple. He's at MIT. And when you see the people who suffer the most, they are uniquely equipped to sort of solve a given problem. And that's our target audience. So if you're hurting and you know what can be changed but are not able to make that happen, that's where we want to focus, and I'll talk a lot more about it. So who did we build this for? We had the plant scientists who had data, we had the computational folks who were producing tools, but they never really looked at each other eye to eye because they were operating in different ways. And here is sort of where the friction between research and production comes into play. For the computational scientists, they are doing research. For the plant scientists, they want production-grade tools. And you had to sort of make it easy for the computational folks to create production-grade tools. And that's sort of what we set out to do. And we built different platforms, and I'll talk a bit about those, where you could easily do that. And then eventually you want to put it out for the community where they don't need to know the nuts and bolts and how it happens. They just want a task done. So going to computational thinking, and more importantly, computational doing. So this concept actually, Janet Wing, when she's at Carnegie Mellon and when she was at NSF, she really in the 90s pushed for it. This is an important part for the domain sciences and even for, I think, computational sciences, where it's the abstraction, automation, ability, and audacity, the four important A's, and allowing the researchers to establish and manage data-driven collaborations where they could design a virtual organization at a global scale. You'll be surprised how many groups, especially in the life sciences, work across country boundaries and work in teams that are way beyond just your own home institution. And they're fairly organic. And then make efficient and coordinated use of CI resources, cyber infrastructure resources, regardless of where they come from. And they were all sitting on these really nice, at this point, 100 gigabits per second connections. But in their data management plan was FedEx and UPS because they ship hard drives. And that's just criminal in today's day and age when you ship hard drives, when you're sitting on 100 gig connections between your universities. Most Research One universities are on 100 gig connections. And there's a last mile problem that we'll talk of. And so adopting the best practices from science domains where some of these challenges were solved. The astronomy community has done something good, particle physics. So the life science community had to sort of look at it and say, what can we cherry pick and steal from others or learn from others so that we can do it better? And then finally, the emphasis on self-provisioning and extensible open source infrastructure, and then bring in the engagement from the SAIS community, because these were our neighbors that we were not learning from. And so what are our users looking for? They're looking for something like this. Where do we send them? We send them to Home Depot. Okay? Now, you're not a good friend if you're going to send somebody to Home Depot to buy furniture. And when you give them the answer, yes, there's plywood, there's nail, there's paint, everything's there. You can make your chair whichever way you feel like, right? That's the business we are in. That's all the talks we have heard in the last few days. And with respect to Amazon, I don't mean to, this is my Home Depot for my users, right? I tell them, go here and you can solve your problem. And then when they put the chair together, this is how they feel, okay? Or maybe like this. And this is sort of, I just stuck this in because I like it, this is like wishing IKEA a happy birthday and saying, here's your cake. And that's what happens to our users, where it's like, hey, you want cake? Here's your cake. Doesn't work, okay? And at the end of the day, it's expectation management with technology. And so we were sort of, again, changing the paradigm. And yesterday somebody did bring this up, and I had this in my slides, where our community was used to, I'm going to record this program on this day, and I can only record one channel. And that's the obsession you have, and that's what you're going to do. Now, keep in mind, Xfinity was put together very quickly to address competition from somewhere else, right? We are trying to be like this, and that also has its expectation problems, right? And the last mile issues get in the way, and it's really hard to explain to someone that why can you watch one movie and the other movie is not working, because that might be coming from a different network path. And that happens pretty frequently with my wife, and she's pretty savvy. And then she's like, no, earlier it was easy to sort of blame the operating system or the laptop. Now blaming the cloud is kind of complicated because people just expect magic. So that's one downside I feel of the cloud is, you don't know who to point the finger to in the cloud and say that's that person's fault. But anyway, so there's expectation issues. This is how our infrastructure looks. At the most foundational level, we take hardware resources that come from wherever, don't care. And then these are projects that were around for many, many years. So think of it as I went shopping in NSF's list and said, who does good data management and federated storage? Who does single sign-ons? Where is sort of the, at that point when we started, we had Eucalyptus, but where is the cloud platform? Who does good sort of scavenging of cycles and connecting things together for hundreds and thousands of jobs? And these guys were all doing it for 20 years. They'd gotten gray hair and they'd learned things that we should use. And my staff always teases me and says, you like old people software. And I'm like, old people software is good. It does work. Doesn't mean you have to throw it away. And so we looked at all of these guys, connected them, and said, what are the gaps that make it difficult for our community? And surprisingly, every project that we went to and said, we did this analysis, and this is the gap we realized. Would you make these changes? We'll pay for it. We'll collaborate with you. And every project turned around and said, you know what? Nobody comes and talks to us about this. All we hear is, doesn't work, screw you, and they move on. And you're like the first handful of projects were like, I'm going to stitch all of this together. And you can imagine the fear in my staff's eyes when I said, we're going to write middleware to make this easier for our community. And so that's what we did, and we built foundational service at that level, and we created data stores, which is this plus this on this. And then we created products, which I'm going to talk about very quickly, and that we created on top of it. So ease of use is up. It's very easy here, but flexibility is here. And we allow our users to jump up and down. As you decide you want more flexibility, come down, work at the bare metal level, and if you say, I just want ease of use, and what we realize is even our power users who are straight up, I need the cores, get out of my way, after about a month come and say, I need help with the data part of it. I want to share it with this person who's in this institution. What's the way we should use it? So it was beautiful to see that they could go up and down, and we realized that nobody lives in one of these sections. They all go up and down. And so I'm going to talk about those two. I'm really behind. Okay, so these are the projects. You can see I already talked about them. So people build their own systems, and we call them powered by Cyverse. They consume specific components. They use applications. They build appliances in our cloud platform. They publish. They advocate the use. And more importantly, they build their communities. And then they create learning material that they share. So I'm going to quickly fly through this. I won't touch the science DMZ, but I think that's really important. For those of you who don't know, that's our demilitarized zone for the 100 gig networks and others where we do quite a bit of high throughput work. So let me talk of the data store. This is sort of the backbone of our infrastructure. Doesn't matter what is underlying. This is the data management layer. It offers metadata services. It manages the data lifecycle. And many come to us thinking that they want CPU hours. What they really look for is data management. And this is how it looks. At the center, it's there. And we have the tools, whether you want command line, you want to write your own, you want APIs, Fuse. And yeah, when you look at Fuse, no, it's not just the regular Fuse. There are versions of Fuse that we have created that have parallel capabilities. You can connect our cloud platform, our web platform, send it to HPCs and other grids. The idea is once it's here, it's liberated. And then you can have public and private, and you can see all sorts of interesting things that go with it. The extension to this is we are moving into Syndicate. It's a project with my colleague Larry Peterson in computer science, where we are using sort of the internet to infrastructure and CDNs. But this is going to be a different type of CDN where it's not just distributing the content, but when you make changes, how does it come back to the parent? And so the whole idea of being able to have almost a two-way CDN, if you may, and I'm happy to go into details with anybody who wants to talk about it offline, is how do you now use the existing infrastructure for CDN for science projects? And so we can talk more. Discovery environment being sort of our web interface. You can bring in different things, do your data management. I'll talk a little bit about Docker and how, again, bringing in that technology and making it accessible. If you go to our wiki and say, use Docker, it will very clearly tell you, we want reproducibility. We are not going to allow you to bring your Docker without a Docker file, and this is how you create. So the training for our scientists is not about make a random image and then run it here. No, it's more about make it this way, and once you make it, you get a free web interface, you get notifications, you have the ability to run it on any of your data sets. It's no longer Docker running on your laptop with toy data. This is at scale. And so the next thing is our cloud platform, where we wanted to make cloud great again for our community. And so we were trying to address the usability, collaboration, and allocation. And I know allocation may not be something that you guys are used to because you have a credit card that pays for it. In our case, everybody's fighting for those little dollars. And once you say, here's your share of the cloud and share it with your lab, there's a lot more complications than you would imagine. And so we wanted to make it easy for that to happen. How do you take from your laptop to the cloud? How do you have vetted images? How do you use existing distributed computing? There's a lot more that's talked about the newer technologies, but there is a body of work in distributed computing that's really awesome, and it lends itself beautifully in the cloud. How do you bring that to the forefront for the community? And how do you manage projects? How do you understand how things are being used that you are providing to the community, and how do you connect public and private cloud? So here is an example. Here is the catalog. And if you go into our project and search for it, I'm looking for an application called Quest. I found it. You can see somebody's already integrated. There are few versions of it. And you can see there's a login right there. I click, goes to the single sign-on. Now I can see what resources, where I'm using it. And then this is sort of where we scaled it out and said more people need it. We wrote a separate project. Here is part of our cloud infrastructure called Jetstream. The details are there. It may not be as big as what some of you are used to, but again, this is a flavor. You go to Jetstream, it looks just like our project, but it is a different project, and we gave them all our components, and now they're servicing the engineering and the science community, not just the life sciences. And you can go log in here. The beautiful part is now anybody in the US that's in an academic institution can go and start utilizing it. So this is released to a much bigger community. And here you can see, we tell you how much CPU, how much memory, how much storage, how many volumes, and how much of your allocation you're using, so people get a sense of their utilization and what is up to the point of here is what you're running, where it's running, and then if you want a web shell into it, you want remote desktop, the identity management and everything else is baked into the system. And so we have image management systems. I'm not going to talk of those, but our users can bring in 100,000 by 100,000 images as in pixels and work with all of that in the browser. I'm not going to talk about this. So what's the community building? We have 1,000 genome projects that use it. We have large-scale workflows. And these are user-managed, 25 to 50 terabytes of data, million of CPU hours. You can see some of the people building their things, talking about how they can use our APIs. And that sort of is the fun part for us. The important part I want to talk about is training the scientists. And this is sort of the hard part, where how do you make them realize how to use the infrastructure in an efficient way and then operate at scale and then contribute that back to a bigger community. So we do software carpentry. How many of you know what software carpentry is? Okay. Those of you who don't Google that word and participate and help, it's all volunteer. But in my personal opinion, everybody is a data scientist who's in academia or even not. And everybody is a software engineer in some flavor or not. I also teach a course in applied cyber infrastructure concepts. And the idea is to teach them about these resources, but the most important part is how do you work in team science when the people you're working with don't speak the same language as you? And so we have interdisciplinary teams, and initially when the students come in, you can see the pie chart, they hate people, they don't want to talk to other people, and they're all lone wolves. And then by the time they learn how to work in the class, they realize that communication is key, and teamwork is going to allow them to solve some of these problems. So working with technologists in this area, along with their domain question, is going to really sort of play a role. The students in 2012 annotated a rice genome, and then they had groundwater stuff. They did EMT models. Last year, they did exoplanet hunting. And here's an example of what they were doing. And the researcher said, it takes me months to produce it. I want to take it in hours. That was the goal for the students. They had to be able to scale that along with the researcher. And they were able to do that. This year, we are going to work on Zika and dengue and chikungunya and get a very high resolution understanding on a regional scale. And so building global communities is what we are after. I'm going to fly through some of these things because I've talked about them. You saw these. Just a quick. So our ecosystem is expanding. We started here, and now different people are taking what we have. Here are the people who are paying the bills for them and doing interesting things with the infrastructure. This infrastructure is not just for life sciences. It's expanded well beyond. I'm not going to talk about the network parts, but networking is a big deal for us. And we are working on making it much easier for our community. But the last mile problem is going to hurt most of you here as much as it's hurting us. And we need to fix that, and we need to optimize our networks. And again, I'm not going to cover much of this, as I had mentioned earlier. So we have become sort of a reference model for a lot of communities in the physical sciences, in animal and biomedical. And so this is sort of where I see our community go. I want them to be the superheroes in the Lego blocks that I mentioned. And then finally, if you want to go fast, you go alone. If you want to go far, you go together. And that's a very pertinent African proverb that we subscribe and we firmly believe in, because we are not trying to get 1 or 2 labs to do super awesome things. We are trying to get a much bigger community to change and do things together so that we all go further. With that, I'll stop and I'll take questions.
For questions?
So it's not actually a technical question, it's more of a, putting on my citizen of the world hat. There's a profound challenge that's emerging in not just the US, but globally about reproducibility in science. The idea being that if you put a paper out, you don't just put out your paper and your methods, you put out your code, you put out your example sets and so forth. I was wondering what the take of the researchers of your initiatives been on that, number one, and number two, what are you thinking about in the world of provenance and some sort of global citation or a citation mechanism?
Very good question. Sort of is at the forefront of what we do. So you saw some mention of Docker and containers and VMs and snapshots. What we also are facing with is the reproducibility on the computational part is now becoming a reality. There are still methods that don't lend themselves well, like if you have something that's MPI based and was designed for something that was very specialized hardware, but that's about less than 5% of the code we use. The rest fits beautifully on sort of things that are containers, Docker being one of the flavors, Rocket, choose whatever you feel like. What we are doing is we have an effort called Data Commons, and it's on my slide, where you can take that and export that along with the data components. We issue you a DOI, and you put your code in GitHub, so there's a sort of a time, or any repository and link to it. And then the compute infrastructure where you can reproduce this is given to you as part of it. So when you go into Data Commons and look at it, the container image exported, the file, the Docker file, the recipe for it, and anything that you run in our infrastructure, iRods allows us to embed the metadata. So as a user, you can actually walk through and generate a graph of everything you've done. This file used this program, produced this output, and you can walk back. So you can, if you have an output file and say, how did I get here? You can plot your journey. Now, all of these things exist. We haven't exposed them to our users in a consumable way. Now, we have the provenance APIs, but we realize that giving them a laundry list of what the hell happened to their data, it's really noisy. And so end of the day, if they can reproduce the results and the numeric values that the author did, and then take their data and sort of plop it there, turn some of the knobs, and get an output and give an assessment, that's more valuable to them than giving them reams of or lines of code for reproducibility. So we're sort of trying to tackle that at few fronts. Hopefully that sort of answers your question. And the DOI part is where now there are good data DOIs and other things where they can go to a citation index and understand who's consuming what they produced.
Other questions? So I had one question related to, I would say, like the fundamental idea behind the project. So some of the key goals are to support reproducibility, make it easier for scientists to share, analyze, to all this work. And there are, I would say, at least two ways to do it. One is to really build the whole stack bottom up and really have a whole new infrastructure. One would be to partner maybe with some of the existing cloud providers and build something on top of their offerings. So can you comment on the benefits of going kind of all the way up from scratch?
So I would like to clarify, we did not go all the way from scratch. I showed you in our layer cake all the people with gray hair that gave us the foundation. So we are standing on shoulders of giants. What we also did is create sort of the feeder where as new technology comes in, you can onboard that. And I didn't have a chance to talk of our science APIs where some of the users don't care. Like we were on Eucalyptus, now we are on OpenStack, and if we are sending it to Rackspace or Amazon, they don't care. And that API abstraction layer that we are providing is allowing us to bring in anything new and swap out something that didn't matter much more easily. And from sort of the domain science perspective, we are trying to onboard the community, get used to something, and then learn to peek below the hood and then manage it the way you want. So when I talked of going up and down the stack as well, you can choose where you feel most comfortable for the task you want to do today. And so, we can easily operate with whoever else wants to bring in their wagon and line it up with what we have, and people are going to be able to consume it. The idea is you can never have enough for a community by yourselves. You have to federate, and we are in the business of federating everything. And at the end, I would say, our job is to scale people. It's not about the technology, because every lab, and I'm sure some of you can relate to it from your time in grad school and others, where there's like one or two people who are sort of the engines of your lab, and they can only service that many people. And beyond your lab, every time you go to a conference and come back, I'm sure your lab is freaked out because you are going to add 10 new ideas, and they're like, oh no. And so this is sort of where when you come back with 10 new ideas, your lab's like, yeah, we can take it on. We'll get this from here, get this from here. But the bigger thing is outside your lab, because when you're doing things, how can somebody collaborate with you, and how can you have a much bigger network? And that's sort of our goal, and this is the infrastructure is just a vehicle for us to get to that goal.
How do you deal with public data and private data? Many times, many scientists want to keep some data proprietary for at least a period.
Excellent question. So we have a full continuum of permission models, and our data system is also based on policy and rules. So if a piece of data arrives, whoever brings it in already has the notion of creating a group and who can see it and at what level. It's pretty much like POSIX, if you may, at some level. But then there are certain projects that are obligated to share their data on a temporal time, on a time scale that once you produce this, in 6 months you have to give read access to the rest of the community. The underlying data management platform provides that for us out of the box. But then that is community data. But if you bring in data as yourself, as an individual, not part of a project, you pretty much control it whichever way you want, and you build your own sort of sharing. The part that we haven't really turned on, and we're sort of waiting for that, is we have the understanding of the metadata coverage and how often data is being used. And I think the question was asked, you have S3 full of data, what are people doing to sort of do some house cleaning? And so we run these sort of house cleaning activities, and we're keeping track of it. And then eventually, because we don't want our system to be a backup for your, as in like data dump yards. And so if you're not doing much with that data, or the community is not doing much with that data, either we'll send you a bill, or we'll say do something to get more people to use it. And we are happy to help you make that happen.
So iRods and containers and VMs, I mean, I can see how this can kind of work for things on the gigabyte scale, but how well does it really work on the terabyte or even petabyte scale? Is that where the CDN needs to come in? How do you avoid moving data all over to get it to where the compute is happening?
Okay, so maybe I'll answer it in a few layers. The first, terabyte scale, that's pretty standard. These things do work. As in managing terabyte file sizes. Rather, it's been sort of one of those funny occurrences when I was on a conference call on a WebEx with one of the community members who was asking questions, and they picked up a file that was 400 gigs, and we were sort of seeing it on screen. And then I said, you do realize that the problem you're complaining about, this file is 400 gigs. It's not 400 megs. And because it was an easy web interface, and they could also do something on, and so we have sort of elevated the expectations of everything should be drag and drop, which is hard. And so I think we sort of reached the terabyte. Our next layer up, where you have hundreds of terabytes, that's when we sort of convert our users to, you have to use a workflow manager. That's data staging involved, and how that's done is what we cover with them. And that's fairly one-on-one, because anything that we put out as instructions are not very helpful. And there's a lot more hand-holding on designing that. How do you sort of leverage a new machine in Xseed that has certain capabilities? And so we rely on workflow managers like Pegasus and Makeflow to allow that to happen, and then for them to manage their computation. At which point Docker and others don't sort of fit in that equation, but we allow them to prototype a lot of that in the container environment, and then the providers of those resources, let's say Wrangler or whichever machine, help them fit things that are going to utilize the specialty of that machine. And then these guys turn the fire hose on with that data onto that system, but Pegasus is now doing all the tracking and managing it and then putting it back into the data store. I don't know if that answers your question.
Any more questions? All right, well, thank you very much.
Thank you. So we are right on time. Now we have 1 hour scheduled for lunch, which is